Welcome. In this session, we'll continue with the discussion on Z transform and let's learn few properties of this Z transform. Now, the first property is termed as the linearity property. So, if I say the Z transform of x1 of n is x1 of Z, and Z transform of x2 of n is x2 of Z, then Z transform of A1 x1 of n plus A2 x2 of n will be simply given as A1 x1 of Z plus A2 x2 of Z. So this is the Z transform of this sum. And if remember, if the ROC of this is R1 and the ROC is the region R2 on the Z plane, then ROC of this sum will be simply the intersection of R1 and R2. Remember, the ROC of this sum will be simply the intersection of these two, and this is referred as the linearity property of Z transform. Linearity property of Z transform. Linearity property of Z transform. So this is the linearity property of Z transform. All right. Now next property, we'll discuss only few, is very important, is the time shifting property of the Z transform. So now before I discuss this time shifting property, let me do one example on this linearity property. Now the Z transform of 2 raised to power n u of n minus 3 raised to power n u of n. What's the Z transform of this? Now we have already studied the Z transform of it is Z transform of a raised to power n u of n is simply 1 by 1 minus a Z inverse if magnitude of Z is greater than a, and we know on the complex plane it simply means if ROC is outside the circle, means whose magnitude is a. That's the meaning. So this is the meaning. Now I use, instead of a we have 2 here and here we have 3. So substituting, so we can write the Z transform of 2 raised to n u of n equal 1 by 1 minus 2 Z inverse when magnitude of Z is greater than 2. So it means we need to write the positive value. I can say simply this is greater than 2, means if the region of convergence of this is simply outside the circle of radius 2. So the region of convergence is outside the circle of radius 2. So this is the Z transform of this. Same way, Z transform of 3 raised to power n u of n can be written as 1 by 1 minus 3 Z inverse if magnitude of Z is greater than 3. In other words, if the region of convergence is a circle whose radius is 3, means if the region of convergence outside this circle. Alright. So this is the Z transform. Now the Z transform of this sequence, which is the sum of these two sequences, can be written as Z transform 2 raised to power n u of n 3 raised to power n u of n can be written as 1 by 1 minus 2 inverse minus 1 by 1 minus 3 Z inverse. You can simplify it, and the region of convergence of this is ROC of this is greater than 2, and the magnitude should be greater than this should be greater than 3. then only these two exist. And I said the region of convergence is the intersection of the two regions. Now you can see the ROC of this is outside the circle of radius 2, and the ROC of this is the outside the circle of radius 3. So what's the common region? It will be simply the common region of these two will be simply the intersection between the two, and that will be a circle of radius 3. So the Z transform of this will be simply this if Z is greater than 3. That's the common region between the two. Alright, so this is the first property. Now in the second property, we'll discuss in the first. Now, in the second property that we are going to discuss is very, very important for us. It's called the time shifting property. Time shifting property of Z transform. Time shifting property. Now, what is this time shifting property? If Z transform of x of n, this property says if Z transform of x of n is x of z, and let's suppose the ROC is R, any region on this Z plane, then the Z transform of, remember this is very, very most important property for us in this course. Z transform of this will be simply Z raised to power minus k x of z. Now you can prove it, it's very easy. It's a two-step job. You can prove it. And the Z transform of x of n minus k means the shifted version of x of n is simply Z raised to power minus k x of z. And the region of convergence of this will be simply entire ROC except z equal to 0 if, remember, if k is greater than 0, or except this, or remember this, or if k is less than 0. So if k is less than 0, then this will exclude this point, and it will be the entire ROC will be the entire R, means whatever is the region of convergence of this x of z, region of convergence of this will be exactly the same, except if k is greater than 0, then the region of convergence will exclude this point. If k is less than 0, means if k is minus 1, minus 2, minus 3, or like that, then it will exclude this point, and it will include the entire ROC that is included by x of z. All right, you can prove it. It's a two-step job. This is given in book, so we don't need to prove. It's a two-step job. You can see the proof from your book. Now let's suppose we want to calculate suppose our sequence x of n is given to us, and let's take the example like this. Suppose this is the z x of n. Then we know the z transform we have already computed. You can compute it again by substituting the value of, let's suppose this is n equal to 0. Sorry, this is 1 minus infinity plus infinity. This is 1 minus n, and to substitute the values of x of n when n varies from infinity to infinity. This will be simply 1 plus 2 z inverse plus 3 z minus 2 z minus 3 z minus 4. So this is the Z transform of x of n when x of n is equal to this. Now the Z transform of x of n minus 2 will be equal to simply, from this shifting property, it will be simply Z raised power. Now first of all, what's the region of convergence of this? You can see the region of convergence of this is entire Z plane except z equal to 0 point. So except this, it's the entire Z plane, means the Z transform will exist everywhere except when z is equal to 0, except on this origin. So it will exist for all values of z. Now the Z transform of this will be simply z raised to power minus 2 x of z. So z raised to power minus 2 is there, and x of z is already calculated, so we can multiply the two. So this is 2 z minus 3 plus z minus 2. Now taking z minus 2 inside, this will be simply z minus 2 plus 2 z minus 3 plus 3 z minus 4 plus 2 z minus 5 plus z minus 6. So again the region of conversion, this is entire z plane except z equal to 0, except this. So z should not be equal to z. So z should not be equal to entire z plane except z equal to 0. Same way you can compute the z transform of x of 3. You can check it from this. It will be simply z raised power 3 so z, and z raised power 3 gets multiplied with this z transform. So it is 1 raised power 1, 3 raised power z minus 2, 2 raised power z minus 3 plus z raised power minus 4. Now taking z inside, so this will be z cube 2z, so this will be 2 3 minus, so this will be z raised power 1 2 plus cube and cube will cancel, this will be z raised power minus 1. So this is the z transform of x of n minus 3, and you can see the region of convergence of this again is entire z plane except, see, this z equal to 0 is not included in the original ROC. So that's again not included here because if z equal to 0, this quantity becomes infinite. And it also excludes z equal to infinity point. If z equal to infinity, then the z transform does not exist. So you can see when k is less than 0, means you can see k is here minus 3. K is minus 3 because we can write it x of minus infinity. So we can write it as x of m minus 3. So k is minus 3. So when k is negative, the z equal to infinity point is excluded from the region of conversion. So this is the z transform of a shifted version. So time shifting property of z transform. This is very, very important. You must memorize this also. This is very, very important. All right, next what we are going to do, we are going to see the convolution property of Z transform. Convolution property of Z transform. Convolution property. Now what does it mean? Means if x of n is defined as the convolution between x1 of n and x2 of n. This is the convolution operation. So if x of n is defined as convolution between x1 n and x2 n, and remember if x1 n has the z transform as x1 of z and x2 of z is the z transform of x2 of n. Then the z transform convolution property says that z transform of x of n, which is defined as the convolution between x1 of n, means the convolution of this, the z transform of this convolution will be simply the product of these z transformers. This is the beauty of transform theory actually. It converts the convolution operation to a multiplication operation. Convolution operation has four operations in it. It has shifting, addition, multiplication operation and reflection operation embedded in it that we have already seen in the this convolution formula. There are 5 operations embedded actually in convolution sum, but here you can see this is simply a multiplication of the transformed signals. So it converts this convolution operation to a simple multiplication operation. All right, so this is the property. Now let's prove this. So the z transform of x of n, which is defined as the convolution of x1 of n and x2 of n. Now we know convolution, we can write the convolution between x1 and x2 n. If you remember this is simply k running from minus infinity to infinity, x1 of k, x2 of n minus k, n minus k. So this is how we define the convolution. So the convolution, so we can say this is the Z transform of this convolution sum. And using the definition of the convolution, using the Z transform, this will be equal to summation and running from minus infinity to infinity x of n. X of n is this time equal to this sum. So this will be simply k running from minus infinity to infinity x1 of k, x2 of n minus k, z raised to minus n. Instead of this, we use it to have x of n, but x of n is this time this big convolution formula. Now we can write it like this. You can see this summation is independent of this. So I can take first the summation inside, means I can take this summation outside. So k is running from minus infinity to infinity and goes from minus infinity to infinity. And I can take x1k outside with this sum because this sum is independent of k, so it will be x of n minus k minus n. Now what is this? What is this part of the formula? What is this? Can you check it? What is this? This is simply the shifting property of Z transform. Means if the Z transform of x2 of n is simply written as x2 n, z is minus n, and go from minus n to infinity, then Z transform of x2 of n minus k will be simply x2 of n minus k will be simply n running from minus infinity to infinity x2 of n minus k z raised to minus n, and this we know is the shifting property. From here we have already solved it. We know the Z transform of this was simply z raised to minus k x of z. So here instead of x of z we have x to z. So substituting this we can write it as into infinity x1 of k. So this will be z raised to minus k x2 of z. x2 of z. Now you can check x2 of z is independent of this now. So x2 of z is simply independent of this sum. We can into infinity x1 of k z raised by minus k. Now have a look at this formula. Have a look at this. What is this? This is Z transform of x1 of k. Only difference is k is instead of n we have now k. Instead of n we have k. So this is the Z transform x1 of k, x1 of n, x1 of n, and we can write it as Z transform. So you can see the Z transform of x1 of n convoluted with x2 of n is the product of the Z transform. Is the product of the Z transform. This is very, very important property of transform theory, and this is true for Laplace transform, Z transform, and Fourier transform. Now, one more thing. Whatever Z does for discrete time sequences, identically we have the Laplace transform for continuous time signal. Whatever Laplace transform is doing to continuous time signal, Z transform does identically the same thing to the discrete time sequence. Means like the same job. Now the third and final property that we will discuss is fourth property actually, I guess, is the initial value theorem. The initial value theorem. Now this term says if the Z transform of x of n is x of z, then we can get the initial value. Initial value means x of 0, means when n is equal to 0. Initial value from Z transform means we can get it like this. If limit z approaches to infinity, x of z. So Z transform of this will be equal to this, and remember this is true only if x of n is a causal sequence. Causal means if x of n is equal to 0 for n less than 0. That's the meaning of causal sequence. So if that's the case, if x of n is a causal sequence, then you can write the initial value of this x of n will be equal to, you can compute that from Z transform. This is asked sometimes in the gate, so we can write it as, we know the Z transform of, to derive this property, we can write the Z transform of this like this. So the Z transform will be, Z transform will, we know from definition is given as minus infinity x of n, 0 is for minus n, and if x of n is causal, it is 0 for magnitude time, so we can write it as from 0 to infinity x of n, 0 is for minus n. Now this is true because this sequence is 0 for magnitude time, so we expanding this, so this will be x of 0, 0 for 0, x of, this will be x of 1, 0, sorry, this will be x of 1, 0 is for minus 1, x of 2, 0 is for minus 2, put n equal to 0, 1, 2, 3, and so on. And this is equal to 0. Now we can write it as 0, x of 1, 0 is power minus 1, plus x of 2, 0 is power minus 2, and so on. Now, if so, this is our x of z of this signal. So this is the x of z of the signal. Now you can see if I take limit z tending to infinity on both sides, if I take the limit. Now you can see if I say z tends to infinity, this quantity is 0, this quantity is 0. These quantities, and we are left with x of 0, and there is no z there, so we can write it as limit z tending to infinity x of z is equal to x of 0, because rest of the quantities will be 0 if I take this limit. So you can say x of 0 is equal to, x of 0 is equal to limit z tends to infinity, and this is the initial value term, and you can get the initial value of this signal from the Z transform. For example, if the Z transform of the signal is like this, if the Z transform is 2 Z inverse plus 3 Z inverse, if this is the Z transform, then what's the initial value of the signal? Initial value of the signal is limit Z infinity x of Z, so value of x of Z, you can write 2 Z inverse plus 3 Z. Yeah. Now when z tends to infinity, this is 0, this is 0. You can check, this will be 0, 0, so this is under 1, that's 1. So the initial value of the signal is 1. So the initial value of the signal is so. Alright, so this is how we compute the Z transform of these signals, and we define several properties here, and we define several properties. All right, in the next session, we'll see how to compute the inverse Z transform of this term Z transform.